This is the third lecture for Wednesday, April 22nd. I know this is a long haul, but originally homework 21 was supposed to be for one lecture, and homework 22 was supposed to be for a whole nother day. And because of the extension of spring break, I had to condense all of this material down to only one day. But I did delete a whole lot of problems from the original MyOpenMath assignments. That's why all of the ones online now for homework 21A, 21B, and homework 22 say abridged. So they are shortened. I also deleted problems from the written work. So if you compare the original syllabus to what I have assigned now in the new syllabus, the one that came out in March, you'll see that a good number of problems are missing. But I still have to cover these concepts because they're part of the requirements for UAA for what I need to cover in this class. So today we're moving on to 9.4, logarithmic functions. And so this lecture is going to cover 9.4, 9.5, and 10.1, which will get you through homework number 22. Okay, so let's start first with the meaning of a log. What is a logarithmic function? They're called logs for short. Here's the bottom line. The log function is the inverse function of the exponential function. Okay, so go back to, let's just move down here for a second. Go back to the original exponential function we were discussing. Here's your basic default, like let's this be y equals 10 to the x, okay? Here's your basic exponential function. This function is a one-to-one function, right? So this function has to have an inverse. There has to be a function that will allow all of the y values to go back to x. Now, if you were to have this function and I told you to switch x and y, okay? Let's say you're trying to figure out what the inverse function is and you switch x and y. And then you try to solve for y. How are you going to solve for y when y is up in the exponent? The only way to get an exponent variable down is with a log. When I taught high school, I said it this way. Here's Rapunzel stuck up in the tower, and the only way to free the princess from the tower is to ram the tower with a log. So as you go into higher math, you get to use logs to free the princess from the tower, to free the variable from the exponent location. So the inverse function is what's going to happen when you get y by itself. And it was the way that we write it, if I want to get y by itself here, this ends up being y is equal to log base 10 of x. This is the way that we write it. The graph of the exponential function is this one. The graph of the logarithmic function, it looks like, here, let me erase this part right here. Here's your exponential function, and here's your logarithmic function, okay? So the log function looks like this, the exponential function looks like this. One thing I didn't mention, but is always true, here's the line y equals x. All right, let me try that again. That marker did not work. Oh, I need a different color. And I'll have to use black. Okay. This dotted line right here is the line y equals x. A function and its inverse function are always reflections of each other across y equals x. So pretend that y equals x is a mirror. This function is going to be the mirror image of that function. Okay, so now let's look at the definition of the log. What is the log? The log, you just need to memorize this, or not memorize it, you can have it in notes. To go back and forth between these two situations, one thing you want to notice is that x has to be positive. The reason x has to be positive is because the domain of the log function is only positive x values. For the original exponential function, the domain is all real numbers, right? But the range of the original exponential function is all positive numbers. So the domain and the range swap here. Here, the range is all real numbers, but the domain is only positive numbers. So x has to be positive. B also has to be positive. We talked about b. If b is between 0 and 1, it's exponential decay. If b is greater than 1, you have exponential growth. B can never equal 1 because that would just be a flat line, and that's neither exponential growth nor decay. So if that was a little confusing, that was just a conceptual thing. What you need to do is you need to be able to use this definition of a log. So let me pull up the first MyOpen Math problem that you need. So from homework number 22, the first MyOpen Math problem that you are dealing with is you have log base b, and the number for my problem is 6, and this is equal to 3, and we need to rewrite it from logarithmic form into exponential form. And here's the way you do it. If you want to convert from a logarithmic form to exponential form, the down low b, the base of the log, is also the down low number here, the base of the exponential function. So the base of the b will be the same thing as the base of the exponential function. What switches positions are your x and your y. Okay, so here it looks like b to the x. It's not b to the x. It's log base b of x. Okay, you pronounce this log base b of x. But these two are going to swap spots. So what we do, the down low number is still b. These two are going to swap. Okay, so instead of what it looks like here, it looks like b to the 6th, but we're going to swap these, and so we get b cubed is equal to 6. So what we're doing is just learning how to go back and forth between these forms. You don't have to be an expert at logs. All you need to know is how to go back and forth between these two forms. Okay, so now let's look at the second question. Here you have, in question number 2, log base 7 of 49 is equal to 2. And we need to rewrite that into exponential form. Okay, the down low number here, the base of the log, is the same as the base of the exponential. So the down low number is still the down low number, and then these two swap. So it becomes 7 squared is equal to 49. That should look familiar, right? 7 squared is equal to 49. So this is the exponential statement that's equivalent to this logarithmic statement. So we're just using the definition of the log to go back and forth. Okay, question number 3. Here we're given an exponential form. B to the 6th is equal to 3, and we need to write this in logarithmic form. So to write it in logarithmic form, you have log of base b. Remember, the base of the exponential is going to be the same as this, and then these are going to swap. So of 3 is equal to 6. That's how you go from exponential form to logarithmic form. Question number 4. Question number 4 has a part A and a part B. We are taking exponential form and going back to logarithmic form. So in part A, we have 3 cubed is equal to 27. So how do we write this as a log? Here's the down low number. Here's the base of the log. is 3. We swap the position of these two numbers. Log base 3 of 27 is equal to 3. That's it. And then for part B, we have the equation 10 to the negative 4th is equal to 0.0001. And we need to rewrite this in logarithmic form. So here we have a log with a base of 10. Switch the positions of these two numbers. 0.0001 is equal to negative 4. FYI, the log with the base of 10 is called the common log. And the common log actually does not need to be written with its base. So if you ever see a log without a base, the assumed base is 10. So you can actually rewrite this as log of 0.0001 is equal to negative 4, and whether you include the base 10 here or not, it's the same thing. So anytime you see a log without a base, it's actually the common log. And so the implied base is 10. In fact, the log button on your calculator is the common log. So the base of the log button on the calculator is 10. Okay, so that was question 4. And now on to question 5. Question number 5. Let me get question number 5 up for a second. Question 5. Log of 0.1 is equal. Now, you can just type this in the calculator if you want. You see here? There's no base. So what did I say? When there's no base, it's the common log. And the common log is the one on your calculator. So you can just type this in the calculator. Type into calculator. Just type log of 0.1 onto the calculator. The log button is to the left of the number 7. L-O-G, log. Log 0.1. Log 0.1 is equal to negative 1. Ta-da! Like that. Okay, so you could just use a calculator for number 5. Number 6 is also a calculator question. Here we have the common log again. So here we have log 4384. Again, the base is 10. Let me fix this. So we just type this in the calculator, and this one, since it's not a power of 10, you're going to need to have a decimal approximation. Log of 4384, and it says to round to the nearest thousandths. So this is about 3.642 if I round to the nearest thousandths. Okay, so now we're just going back and forth, right? Now we just learned how to find the log button on the calculator. So now let's look at how to solve some log equations using this definition of log. Number 7. Log base 4 of x is equal to 2. So we solve this. How do we solve this equation? Change it from logarithmic form to exponential form. If you change it, you end up with this. 4 is the base. Swap the location of x and 2. This is logarithmic form, this is exponential form, and now you can see clearly that the answer is x equals 16. That's all you have to do. Just be able to switch back and forth between logarithmic form and exponential form. Question number 8. Log base 3 of x is equal to negative 3. So what do? This is the base, 3. Then this number across the equal sign becomes the exponent. 3 to the negative 3 is equal to x. Now 3 to the negative 3, remember, is the same thing as 1 over 3 cubed, right? And that's the same thing as 1 over 27. So x is equal to 1 over 27. So notice that that's an exact answer. That's not a decimal approximation. Okay, so that takes care of 9.4 content from MyOpenMath. There is one more thing we need to cover, though, and that is how to do the self-check 9. Okay, so it's really quite simple to do self-check 9. You just do exactly the same thing as example 9, but change the number. So let me walk you through example 9. Okay, so on page 796, example 9 says that we have a lake, and the lake is stocked by the Fish and Game Department, and they are stocking it with 250 hybrid bluegill, and we want to know the number of bluegill in the lake after a certain amount of time. And so the number of bluegill in the lake as a function of time is given by f of t equals 250. Here are the original bluegill. Plus, here's the growth, 400 times the log of t plus 1, where t is the number of years since the lake was stocked. So here's the amount of bluegill, and then t is the number of years. And so we want to know what is the bluegill population after 5 years. What you'll be doing in self-check 9 is you won't have the exact same equation, but it will be the same type of equation. Instead of bluegill being stocked in a lake, you have a rancher stocking his pond with catfish. So you're going to have a very structurally similar situation. We want to know the number of bluegill after 5 years. So f of 5 is equal to 250 plus 400 log of 5 plus 1. So this is what you do for self-check 9, is you're going to write out the equation that is given to you, the catfish equation, and you're going to replace t, time, with the number 3, because in self-check 9, you want to know how many catfish are in the pond after 3 years. In example 9, it's how many bluegill are in the lake after 5 years. But either way, it's the same type of problem. Then you just type it in the calculator. 250 plus 400 times log 5 plus 1 is 6, so log of 6. And then I end up with 561. It's reasonable to round to the nearest whole fish. Okay, so 561 bluegill. So don't give me a fraction of catfish. Round to the nearest catfish. Okay, so that covers 9.4, and next we move on to 9.5. Okay, so 9.5 is base E, exponential and logarithmic functions. One of the transcendental numbers that you've already been introduced to is pi. Pi is not even just an irrational number, it's something even beyond irrational, and it's transcendental, which means that it's a number that cannot even be solved for using an algebra equation. Another one of those is E, and the definition of E, when I would give the definition of E lecture when I taught calculus. It took a full hour to explain what E was to a calculus class. So what you get to do is just accept that E is a number. It's approximately, and you can find this on your calculator, to find E, go to the number 4. To the left of the number 4, there is a button that says LN. And then above LN says e to the x. So if you type in e to the first power on the calculator, you get about 2.71828 la 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 la. So E is actually named after this guy, Leonhard Euler. That's pronounced Euler, not Euler. And he's the one who actually figured this out, and so E is named after Euler. That's why it's E. Just because of Leonhard. Good old Leonhard. Anyway, what is E? E is the number that is sort of, you might think, like the magic number of nature that is used for what is called continuous compounding, okay? So when we did compound interest, we said, okay, I want to compound monthly. I want to compound weekly. I want to compound daily. When interest is calculated, it can be calculated at these very incremental defined periods of time. But when you put bacteria in a petri dish, you don't tell them, okay, I want you to grow on the hour. Sorry, you're only able to reproduce on the hour, because I'm going to compound this hourly. No, instead, nature, whether it's bacteria in a petri dish or the drug content of somebody in somebody's blood content in their bloodstream over time, that is a continuous growth or a continuous decay. And continuous growth and continuous decay happens continuously. And if you compound continuously, you actually end up having to use E. So the exponential function y equals 10 to the x is the common base. But if you have the exponential function y equals e to the x, this is the special base E exponential function. And the inverse function is called the natural log, okay? So it's y equals L n of x. This is called the natural log. Log natural. I'm sure that this is Latin or something, and with Latin and French and Spanish, the adjective comes after the noun. So natural log is pronounced Ln. Ln. And that is on your calculator right next to the number 4. In fact, that's how you find the e to the x. You find the e to the x by finding the Ln button. That's the natural log. So the natural log is going to be used to solve natural growth. Okay. Now you can convert back and forth between log base 10 and log base of e through a variety of means, and that's how the bluegill problem was still able to be used. You could still use the log base 10 for the bluegill problem, but you see that the Ln is going to be used a lot elsewhere. Now let's look at how to convert back and forth. Since this is the exponential function, the exponential function base e's inverse function, the base is actually e. So this is the same thing as log base e of x. So let's look at a MyOpenMath problem. Here you have question number 9. And in question number 9, we have the equation Ln of z is equal to -3. So what we want to do in order to solve this equation is to rewrite it from logarithmic form into exponential form. What is the base of the natural log? The base of the natural log is e. So this is equivalent, base is e, to e to the -3 is equal to z. Now this you're going to have a decimal approximation. So you type in e to the negative 3, and you get about 0.0498. Okay, so enter solution as a reduced fraction. Oh, okay, we can write that as a reduced fraction. You just take e to the negative 3 and write it as 1 over e cubed. That's a reduced fraction, 1 over e cubed. The decimal approximation is here, but if you want just the reduced fraction, e to the negative 3 is 1 over e cubed. Okay, so now we're going to look at interest rate compounded continuously. The compound interest formula is pretty complicated, but the continuous one is not. Okay, so continuous compounding uses a very simple formula. There used to be a shampoo called Pert, and this is how I remembered this. You just use Pert. P is the principal, the original amount that you're investing. E is the number E on the calculator. R is your interest rate, and T is the amount of time. So in question number 10, it says, find the time it takes for $9,000 to double when invested at an annual rate of 2.3% compounded continuously. Okay, so I am investing $9,000. $9,000 is getting doubled. So if you double $9,000, that turns into $18,000. The interest rate given to me is 2.3%, which is 0.023. And then time. So find the time it takes to double. Now solving this equation actually takes more advanced algebra. So how are you doing it? There's a handy formula that you can use to bypass the fancy algebra needed for this, and it's on page 808. So on page 808 of your textbook, it says that doubling time, there's a formula for doubling time. The formula for doubling time is T is equal to ln of 2 over r. So that's very handy. This only works for doubling time. If you want to triple it, or you need to grow 9,000 to a different number other than just its double, you don't get to use this formula. So this is only a doubling time formula. And you just take ln of 2 and divide it by r. So the interest rate, there's your r value right there. So take ln of 2. Make sure you close the parentheses before you divide by 0.023. And if you type in ln of 2, close the parentheses, divided by 0.023 into the calculator, you're going to get that the time needed is approximately 30.14 years. So if you only have an interest rate of 2.3% and it's compounded continuously, it's going to take about 30 years for it to double. So you can do this same procedure for the first half and the second half of Part 10. Part 10 is going to have you take two different amounts of money and see how long it takes for them to double given a certain interest rate. Alright, so that covers my open math, and then the only other thing we need to do for this lesson is to understand the one word problem that I have assigned to you from 9.5, and that's self-check question 3. And self-check question 3 is based off a baking problem. So it just follows example 3, so let me explain example 3. So example 3, on page 804 says that a mother takes a cake out of the oven, and there's a temperature. See, capital T means temperature, lowercase t is time. Temperature as a function of time, how long it's going to take to cool off. Room temperature is 68 degrees, and then it's plus 220 e to the negative 0.18 t. So T is Fahrenheit after it's cooled for T minutes. And you're going to have to do, for self-check 3, the temperature after 10 minutes. But for the example, they said 20 minutes. Okay? So what is the temperature of the cake after 20 minutes? Well, you just plug in 20 for lowercase t. And for self-check 3, you just plug in 10. Then you type this into the calculator. And when you type it into the calculator, you get about 74 degrees Fahrenheit. So when you do 10 minutes, think about this. If after 20 minutes it's 74 degrees, after 10 minutes it's still going to be hotter than that, right? So make sure that your answer is hotter than 74 degrees. And of course the answer is in the back of the book, so you should check your answer. Okay, so that covers 9.5, and the last section we need to cover is 10.1. So 10.1 covers the circle and the parabola. Originally I did have homework for the circle and the parabola in 10.1, but I've narrowed it down to just the circle. So let's understand first the generic formula for a circle. The circle's equation. The circle equation looks like this. You have parentheses x minus some number h squared plus y minus some number k squared is equal to r squared. And these h and k are the coordinates for the center of the circle. H, comma, k is the center of the circle. And then the radius of the circle is r. Okay, so let's walk through 5 problems. We're going to start with the MyOpen Math problem. First one is number 11. So number 11, we're given the equation x plus 7 squared plus y plus 8 squared is equal to 90, and we need to determine the center and the radius. Okay, now remember, the center is h comma k. It's what we have here and here, but it's the opposite, okay? So x minus h here, that would be x minus negative 7. So take the opposite of this number. If it says plus 7, the h value is negative 7. Okay, so here the center would be negative 7, and then take the opposite here, negative 8. So it's that simple. Just take the opposite of this number and the opposite of that number, and that gives you the center. Now for the radius is r, right? And so the number over here on the right-hand side, 90, is r squared. Okay? So if 90 is r squared, how do you solve that equation? You take the square root of both sides. But you don't need to do plus or minus, because plus or minus is not going to be your radius. You only have a positive. So when you take the square root of both sides, you get r is equal to the square root of 90. But you need to simplify that. So r simplifies then to 3 root 10. Okay, so that's the center, that's the radius, that's how you do question number 11. So next, question number 12. we are given x minus 1 squared plus y plus 2 squared is equal to 1, and we need to graph it on MyOpenMath. Okay, so first what you need to do is you need to figure out the center and the radius. So the center, you're going to take the opposite of these numbers. If it says minus 1, you do plus 1. And if it says plus 2, that means minus 2. So the center is at 1, negative 2. This is r squared, and of course the square root of 1 is 1, so the radius is 1. So what we need to do is graph a circle that has a center at 1, negative 2, and a radius of 1. Well, do not graph the point 1, negative 2, because that's the center of the circle. That's not on the circle. What you need to do is go over to 1, negative 2, and then move 1 away from that number, and you'll end up at the point you need to be at. Okay? But the way that MyOpenMath does it is actually you do plot the center first. You go to 1, negative 2, you plot the center, and then you go 1 over to the right, the left, up or down, and then you plot the second point, and it will graph it for you. But when you're graphing it, if you graph it by hand, you go to 1, negative 2, you don't put a dot here, except maybe just like a little dot to tell you where you're at. And then from 1, negative 2, you go 1 up, 1 to the right, 1 to the left, and 1 down. And those 4 dots, when you connect the dots, give you your circle. On MyOpenMath, you plot this one first, okay? So your first point that you plot on MyOpenMath will be your center. And then your second point is any other point the radius distance away from the center. So you could go 1 to the right, 1 to the left, 1 up, or 1 down from the center, and it will graph the circle for you. So it's pretty straightforward graphing. Now there is one multiple choice question on the final exam on circles. You have to determine the equation of the circle given a graph, and we'll do that in question number 14. So question number 13 gives you information. Question number 13 gives you the center is negative 2, 4. And then it tells you that your radius is 13, and it asks you to write the equation of the circle. So remember, you just plug in negative 2 for h. Negative 2, when you plug this in, minus negative 2 becomes plus 2. Make sure that this is a plus sign. And then y minus k, y minus 4 squared. And then this is r squared. So just take your r value of 13 and square it. And ta-da! There you go. That's how you do. That's how you take the center and the radius and you transform it into the equation of the circle. All right. So now question number 14 is like the multiple choice question on the final. Question number 14 gives you a graph. And in my problem, the graph goes from negative 1 up to, at negative 1, from 0 all the way to 6. And then over to positive 2. And then back to negative 4. So what you can do is you can eyeball your graph. That looks like a football or something, I don't know. Find your center. So my center is going to be halfway, right? So if you were to like imagine this X through your circle, the center is going to be right here. So my center is at negative 1, 3. So I'm going to make the observation that my center is at negative 1, 3. And then once you know where your center is, just figure out your radius by counting boxes, right? So if you go from here to here, that's 1, 2, 3. Or you could go from here to here, and that's either, no matter which way you go, from the center down to the right, up, or to the left, I see that I have a distance of 3. So that means my radius is 3. So then to write the equation, all I have to do is plug in negative 1 and 3 for h and k, and plug in 3 for r. So my equation is x plus 1 squared plus y minus 3 squared is equal to 9. I just plugged these values right here into that. So this should be pretty simple. You should be able to tell where the center is. It's in the middle. Figure out the distance from the center to one of the edges, and that's your radius. Plug it into this formula right here. You can have a page of notes on your final, so you can do that. And of course on the homework you'll have access to that one. Okay, now for the last problem we have to do, this is the hardest problem of all, and I would have deleted it except that specifically I was told in the course content list that I'm supposed to cover equations of the circle with completing the square. So you have one problem like this, and it's self-check 3 on page 861. So example 3 can walk you through all the steps. I'll walk you through example 3. So example 3 on page 860, we have x squared plus y squared minus 4x plus 2y minus 11 is equal to 0. And this is supposed to be a circle, but we need to write it in the form of a circle. So what you want to do is first group together the x's, group together the y's, and throw the constant on the other side. So if you group together the x's and group together the y's and throw the constant on the other side, it looks like this. Okay, so I've rearranged it so that the x squared is still here. The negative 4x I've moved over here. So what I have here are my x's grouped together, and then I rearranged it so that my y's are grouped together, and then lastly I have the constant on the other side. And this is where you use completing the square. So what number do you need to add to these to make it a perfect square? Remember, this number right here is going to be b over 2 squared. Same thing as here. But there's two different b values. This b value is negative 4. Negative 4 divided by 2 is negative 2. Negative 2 squared is 4. So I'm adding a 4. Over here, the b value is 2. 2 divided by 2 is 1. 1 squared is 1. So I'm adding a 1. And 4 plus 1 is 5. So to the left-hand side of the equation, I have added a 5, which means I have to add a 5 over here on the right-hand side. And now I just have to turn these perfect square trinomials into a binomial squared. So this one right here is going to be x minus 2 squared. This one right here is y plus 1 squared. And then 11 plus 5 is 16. And so we're supposed to now graph it. In order to graph this, we have to identify that the center is, of course, then at 2, negative 1. And the radius is the square root of 16, which is 4. So then what you do is you put a little XY chart for yourself. Use graph paper. Here's negative 5. Here's positive 3. Here's positive 6. here is -2. Okay, so the center of my circle, so let me zoom in here so you can see this really well. The center of my circle is at 2, -1. So 2, -1 is right here. And then the radius is 4, so I need to go up 4, to the right 4, to the left 4, and down 4. You use graph paper and the circle will look a lot nicer. Okay, now you connect these. Remember, this is a circle, it's not a diamond or a square. Connect your dots to make a circle. The dot in the middle is actually not part of the graph. It was just there to guide you. But that's how you graph a circle. The hard part, though, was not graphing the circle. The hard part was completing the square. So anyway, that is walked through in detail on page 861. So you can look at page 861. And that wraps up the last lecture of the course. So congratulations, you made it to the last lecture. Good job. And I will see you again for the final exam review.